Dr. Ojha. Dr. Ojha is Animesh Kumar Ojha is Associate Professor and ex-head Department of Physics, MNIT Allahabad. And his research area is both experimental and theoretical. On experimental side, he is doing the synthesis and optical properties of graphene quantum dots, and energy storage, particularly supercapacitor, photocatalytic materials, synthesis and studies of size and shape-dependent optical and magnetic properties of low-dimensional materials. On theoretical side, that he is using the DFT, that is dimensional function theory, studies on the molecular association, that is hydrogen bond and other weak interactions, designing and simulation of organic inorganic hybrid materials for the solar cell applications. So to his record, that he is a Alexander von Humboldt fellow, and he has visited Germany many times, and he has visited Germany also in DST Diet Fellowship. Further, he has attended the Nobel laureate meeting in Germany in 2008, and he has visited Germany again in 2012 in DFG INSA Research Initiative grant. So he has visited this University of California, USA, and many times, that as I have stated, that he is in visited this Germany. He has guided 8 research students and PhD students, and 3 students are working under his supervision. He has published so many good papers in experimental and theoretical side, and completed many projects. So under his dynamic leadership, that department has grown multidimensional, and we are continuing in the same direction. So now I am making a presenter, Professor Ojha. So please, yeah. So you can continue now. Now over to Dr. Ojha.
Thank you so much, sir, for your warm introduction. And I would like to say it's a very vast introduction. And I'm thankful to you for giving me opportunity to talk about the work which has been carried out for last few years in my research group, and that are basically based on the how to harvest the solar energy efficiently, and how to store it. So this talk I have divided into 2 parts. So I will be talking first how to harvest the solar energy efficiently, and then how to store it. Okay. So let me first. So thank you once again, sir, for your invitation to deliver talk in this faculty development program. Let me share the slide. I hope it is visible to everyone. Is it visible?
It is, yes, it is visible.
Yes,
it is visible now. Visible.
Okay. Thank you so much. Thank you so much for the prompt response which I received from all of you. Okay, so the title of my today talk is Designing of Materials for Solar Energy Harvesting and Energy Storage. Okay. Before I before I begin my talk, I would like to ask a question: why energy is so important in our life? And the answer which I am expecting from all of you is it is important in our daily life because it is a basic human need. Nowadays, okay, and we use energy not only to operate electrical appliances, but we also need it for the industrial development as well as the overall development of the country. Okay, and therefore one can say that energy is an essential part of modern life. Okay, and therefore as we are using it in a very vast manner, these cause fast increase in the global energy consumption. The most of energy that we consume is produced by the conventional energy sources, for example, coal, nuclear energy, and oil. These sources have adverse impact to environment in general and human health in particular. And therefore, nowadays, an immense increase in the research activities towards producing clean and renewable energy is observed worldwide. In this, and therefore, in this presentation, I'm going to talk about how to harvest solar energy efficiently as my first part of the talk, and how one can store the produced energy efficiently. That will be the second part of my talk. Okay, so let's begin. I have, before going into detail of my talk, I have a slide which can tell you the presentation outline. Okay, and I have put one slide just to tell to the audience that what currently is being done in my research group. Okay, in the research. And the second part, I'm going to talk about the perovskite solar cell, which is basically a solar cell that harvests sunlight and then convert the sunlight into the electrical energy. Okay, so there are different aspects of this perovskite solar cell. I will start with this designing of material that can harvest maximum energy from the sun, and then so that it can later on convert into the electrical energy efficiently. Okay, and then we'll be talking of this stability, and then I will also have few slides that on this electron transport layer, so that can also be a part of construction of solar cells. So that I will be also discussing. So the first talk, a part of the talk is based on the theoretical investigations which have been done in my research group. And the second part, I'm going to discuss about how to store the energy. Okay, and then for that, I would like to discuss about the supercapacitor, which is has been, which has attracted a lot of attention from the scientific community as a storing material. Okay, as a storing device rather. So these are the two different parts which I'm going to discuss in my today's talk. Okay, so this slide shows that I have two small research groups. One is condensed matter physics theoretical. Here we are dealing with designing of materials for solar energy harvesting and for solar cell application, and then designing of electron transport and whole transport materials for solar cell applications. And obviously designing and simulation of materials for hydrogen storage at 2 temperature. So DFT studies of hydrogen bonded systems. So I'm going to focus on the first two topics of this condensed matter theoretical group, that is designing of energy harvesting materials for solar cell applications, and designing of electron transport and whole transport materials for solar cell application. Now in the experimental condensed matter physics, here we are basically engaged to develop 2D systems such as graphene quantum dots, and their metal oxide composites as electrode materials for energy storage. Okay, and developing stable perovskite material for switching applications. So here I will be taking the first part where we have designed the material to store efficient energy. Okay, as a superconducting a super capacitor material. Okay, so this is the details of my research activities currently being done in my research group. Now, this slide I would like to first discuss because I mean, before you start doing your concept or research plan, one has to know why we are doing that. Okay, so I have put pie charts, several pie charts here that tell about the energy consumption worldwide and the energy consumption by India. Okay, so about if you see that 90% of the world energy is energy requirements are being currently produced by the non conventional sources or fossil fuels, which obviously have the adverse effect as I have already discussed. Only 10% of all energy requirement is being produced from the renewable sources. Okay, India is producing 36% of energy by the renewable sources. Okay, out of which the 10% is from the solar energy, and therefore, if you see that increased demand of the energy globally, it is expected that by 2050, this demand is going to be doubled actually. And therefore, one has to focus to harvest or convert more, more non-conventional energy into the electrical energy. And therefore, for this, research and innovation in the field of renewable energy is necessary for fulfilling the future energy demand. Okay, so here in this talk, I would, as we know that there are several categories of the non-conventional energy sources that produce electrical energy, and that are basically hydroelectric, biomass, and then wind-based energy. So I'm not going to discuss all. I'm going to focus only on the energy which we are going to convert into the electrical energy by solar cell, okay, or solar energy. So here I would like to focus on the solar energy. And solar energy, as we know that it is it has high abundance, low cost, and environmental friendliness are the reasons for rapid development of solar cell research in recent years. Solar energy research has two parts. In my opinion, I have divided into two parts. One is basically how efficiently we harvest the solar energy, and then the second is how efficiently we are storing this energy. So the here in energy harvesting through solar cell, solar cells are a photovoltaic device that can directly convert solar energy into the electric energy. And then these energy can be stored in the energy storage devices for its further application in different fields. Okay, so the storage devices which we know that are battery and supercapacitor. I will be talking of supercapacitor here, and in the first case I will be talking of energy harvesting through solar cell, and the second part the supercapacitor one. Okay, so this is the part one, that is harvesting of solar energy. So the solar cells, in order to harvest the solar energy, solar cells are designed, and it is not new. Everybody knows that the solar cell already exists in the market, but these solar cells are divided into several categories. In general, first generation solar cell, which is consisting of silicon. The second generation solar cell consists of obviously silicon and some semiconductor material like cadmium tellurium. And then third generation solar cell is based on a sensitized solar cell and perovskite solar cell. So I will be focusing on these perovskite solar cells in my talk. Why these perovskite solar cells or dye-sensitized solar cells are required to be investigated or developed as the silicon-based solar cells already exist in the market. So the reason is that the silicon-based solar cells are having complex and expensive manufacturing process to make. This is also costly actually, and the maximum power conversion efficiency of this solar cell has reached to 15 to 20%, and this is actually we have quoted from the efficiency which we received from the device, actually at the device level. And the advantages here of the perovskite solar cells are it is very easy to make, and no complex environment is required here. No complex instrumentation is required for making this perovskite solar cells. And obviously, it is cheaper compared to the silicon-based solar cell. And the power conversion efficiency here can be enhanced further. Okay, so this is why we have focus this talk on only this perovskite solar cells. Okay, and here the one drawback with this perovskite solar cell is that it can't be commercialized due to its poor stability in ambient atmosphere, as well as the efficiency at the device level, which has not been achieved equivalent to the existing solar cell device. Okay, so now these are the two areas on the perovskite solar cells where one can do research and try to find out the solution in order to make this in order to enhance the stability and efficiency better of these perovskite based solar cells. Okay, so let's see here the introduction to the perovskite. So perovskite is a material which have the chemical formula ABX3, where A and B are the cations and X is the halogen or oxygen. Okay, here this A is located within the octahedral cavity, as I have shown in this diagram, that this is the octahedral cavity, and in this cavity this A side cation is located. Okay, so the example of these perovskite materials are SrTiO3, barium BaTiO3, KTiO3, and there are many. These are the one class of perovskite material, and then here you have a CS3NH3 lead I3. Okay, so this is organic inorganic hybrid perovskite material. Okay, so here I will be not talking about inorganic perovskite material. I will be talking of this hybrid, organic inorganic hybrid perovskite material. Okay. So based on its composition, the perovskite material is divided into several categories, where the metal oxide perovskite material, where A and B both are metal cations, and A is AB and X is oxygen. For halide perovskite materials, A, B metal are the metal cations, and anion here is halogen. And hybrid organic inorganic perovskite material, cation A is organic and B is metal cation, and halogen is anion is obviously halogen. Okay, so these are the different categories based on the composition of the perovskite material. Okay, so based on the composition, these perovskites have different properties, and such as ferroelectricity, piezoelectricity, high dielectric constant, non-linear dielectric features, semiconducting, optical, and electrical properties. Okay, based on these properties, all these find applications, find different applications. For example, KTO3 is used as a superconductor, BaTiO3 is used as a dielectric ceramic, ZdFeO3 is used as an antiferromagnetic material, SNI3 is used in solar cell as an inorganic energy harvesting material, and CS3NS3 lead PbI3, which is methyl ammonium lead iodide. This is the hybrid perovskite, and it is used in making a perovskite solar cell. So I will be talking of this CS3NS3 lead I3 as a energy harvesting material in order to construct better perovskite solar cell. So here, what are the properties of CS3NS3 PBI3? So it exists in two forms. One is orthorhombic, another is tetragonal. So tetragonal, and then it converted into the cubic at 330 Kelvin temperature. Okay, this lattice parameter it has A is equal to B, both are same, and because it's a tetragonal, and therefore it has 8.85 angstrom and then 12.64 angstrom. Band gap is 1.4 electron volt, and which is well suited to absorb the light in the visible region. The enthalpy, which basically decides the stability of the perovskite, turns out to be negative 1.1 electron volt, and the till date efficiency at the research level, I'm not talking about the device level, has been achieved to 22.8%, which is close to the efficiency achieved by the normal silicon-based solar cells. Okay, so how this perovskite is basically put in this perovskite solar cell as a energy harvesting material. Okay, so here you see we have electrode, and the other side there is the ITO, and then you have electron transport layer, and then here hole transport layer, HTL, and then in the middle we have this CS3NS3 lead I3. Okay, so here what happens, what is the mechanism that it acts as a energy harvesting material for converting solar energy into the electrical energy. The mechanism is understood by this second diagram, where you incident sunlight, and then what sunlight does, this light is absorbed by the perovskite CS3NS3 PBI3, and then as it is the photon is absorbed, the electron hole pair is generated. The electron will move to the electron transport layer, and then here hole move to the HTL, and then from here HTL it move to the one electrode, and from here the electron will move to the another electrode, and then circuit will be completed, and therefore it basically convert solar energy into the electrical energy. But the question here is that the stability of this device is very, very poor at the normal environment, at room temperature. Okay, therefore how the stability and the efficiency can be enhanced. This can be enhanced by changing this CS3NS3 lead I3 material. Okay, so if somehow we modify this by some different organic inorganic habit perovskite, then this efficiency always, as well as the stability, can be enhanced. The stability can also be enhanced by designing a suitable electron transport layer and hole transport layer. So here I will be focusing to design. Here in this talk, I'm going to discuss about designing of this new perovskite material for enhanced efficiency as well as the stability. And then I have one point or one topic for discussion regarding this electron transport layer. I have also designed one electron transport layer which can protect this perovskite from degradation. Okay, so let's have the another part here. What are the challenges with this CS3NS3 PBI3? The challenges are that it reacts with the water, and then it splits into several compounds. Okay, like lead iodide and then CS3NS3 iodide. Okay, and so this splitting is done because of the water present in the environment. Okay, and okay, so this is then the solar cell, the perovskite solar cell. If you use it at the room temperature, it will be degraded over the time. So this has to be protected actually if you want to commercialize this perovskite solar cell. And the other aspect is to enhance the efficiency, the power conversion efficiency of the solar cell. So these two can be resolved by designing a new perovskite material. Okay, and then how this designing can be done. So this designing can be done. I mean, how one can say that any perovskite, any structure will form a perovskite structure. So in order to basically determine that whether a particular compound which is in the form of ABX3 will form a perovskite structure or not. For this, some factors are introduced. Okay, and there are, some criteria are set to tell that, okay, any structure, any ABX3 type structure will show perovskite structure or not. So that I will be discussing about that particular factor, and then based on that, newly designed perovskites which can basically show better stability as well as efficiency if you use that as a energy harvesting material to make perovskite solar cell. So let's see. This is the first topic which I would like to discuss. The topic is, the title of this work is a new approach to predict the formation of a three-dimensional hybrid organic inorganic perovskites. Now, as you know, any ABX3 compound which you basically design in order to replace this CS3 NH3 lead iodide. Okay, so you must know certain criteria. And here I'm going to tell you what are the criteria by which you can design new material. So the first one is the tolerance factor. So the factor which was initially introduced by some authors, okay, and a long time back. And this factor was used to tell that whether a particular ABX3 compound will have like a perovskite or not. So whether if the value of this tolerance factor that particular compound lies in between 0.8 to 1, this means that that particular structure will form a perovskite. Otherwise not. However, it has certain limitation. This rule has certain limitation, and therefore another factor was introduced by someone, and then that was called octahedral factor. Okay, and this factor was defined as radius of the B cation and radius of anion, and if this value is lying in between 0.414 to 0.723, this means that that particular ABX3 compound will show perovskite structure, otherwise not. Even though this factor has certain limitation, these factors could not explain the nature of the compounds which I have shown here by the red color, and therefore I thought that these two factors are not sufficient in order to determine the nature of ABX3 compound which show a perovskite structure or not, and therefore why these two factors actually failed. So the reason behind it is while introducing these two factors, the scientists assumed that the molecule are spherical in size, which is obviously not true for all the compounds. And then the non-polarizability of organic cations, we cannot say that that particular organic molecule is not polarized. I mean, there are organic cations which show polarizing character. Then third one is neglecting the effect of van der Waals and hydrogen bond interaction. So these features were not included while designing that two particular factors, and therefore our group actually thought over it and then designed a new factor by removing all these points. Okay, and we gave a name of this factor as a homolomo gap factor. and the expression of this factor is given in this slide, and this is basically based on the homoloma gap of the organic cation, then B side cation as well as anion. Okay, and we set the value of this factor which is equal to 0.5 to 1. So if means any ABX3 compound having this factor, this homologo factor lying between 0.5 to 1, that will show perovskite structure. Okay, that will behave like a perovskite. Okay, and the compounds which were not explained using the first two factors, they also got explained the new one which we designed. Okay, so now this is a well accepted factor where if you designing any ABSC type of compound, and if you want to check whether this material will show a perovskite structure or not, that can be checked using this newly designed factor. So it's the one based on this newly factor. I designed. We designed organic a new organic cation, and this new organic cation is designed with the fact that it must enhance the stability of the perovskite structure, as well as also enhance the efficiency of the perovskite solar cell. So how to enhance it? So this was done under the title reshuffling of electronic environment by introducing a new harvesting material, CS3NS2F+. Okay, so what I have done, I have actually removed one H from this NH3. And why I have done it? Because the reason being is that I wanted to have a strong interaction between the two parts of the perovskite. One is basically the inorganic part, which is the case, and then organic part, which is the molecule. So if these two started interacting strongly, then the stability of this structure will be automatically enhanced. And if the one part is resolved, the stability issue is a little bit resolved in this case, and then the other part will check whether what happens to its efficiency. Okay, so let's first go to this part. Okay, so while designing this, this is the original CS3NS3 plus, and then here I have removed one H and put fluorine, because I wanted to make it more polarizable. So it has the dipole moment is more in the second case, then even the dipole moment is increasing in the second case, and the dipole moment further increase in the last case. Okay, so why this more like dipole moment? The more dipole moment is because I wanted to polarize this inorganic part. So once this inorganic part is polarized, then the interaction between organic and inorganic part will be enhanced automatically, which causes to enhance the structural stability of the perovskites. So here I have checked it how it looks like, whether this designed organic cation forms the perovskite structure or not. So based on the newly formed cations, 3 perovskites were generated. One is basically CS3NS2 Fi3. Then here in place of F, we have put 2F. 1H, 2H is removed. 2H are removed here. Now all the 3H are removed. So here you have the H are replaced by fluorine. Okay. And then we calculated the band gap. And so in order to check whether these perovskites, these compounds form the perovskite structure or not, we checked it by the newly designed factor, and we found that the value of beta factor is lying in between 0.5 to 1. Okay, and therefore we can say that these compounds form the perovskite structure. Okay, let's see what are the band gap. Okay, and what are the what are the optical properties of these compounds? What are the stability, structural stability of these compounds? In order to check this, we done density functional theory
the calculations using this fast software. Okay, and look at this. We first calculated the optical band gap, which is basically the essential part for a compound to be used as an energy harvesting material in a perovskite solar cell. And we found that the first compound, I mean this CS3NH2F PBI3, the band gap this is lying close to this I mean the CSNS2F lead iodide perovskite, and therefore this compound is suitable for the perovskite for the perovskite solar cell. Okay, and in this case, however, the other two compounds, has the band gap 0.74 electron volt and 0.17 electron volt. These values are not lying in the range of the band gap for perovskite material required for solar cell application. So we left these two and we only focused on the first one, which is CS3NH2F And you see here that how, okay, so what happens to the interaction between organic and inorganic cation. So you see here, this slide shows the density of state of particular atom involved in the perovskite, this organic cation or even the perovskite structure. So see the first part, which is A, is you see here this in the conduction band. Okay, so this conduction band here, this organic part, the atoms which are in the organic part are not involved in the formation of conduction band. But here in the second case, in the second curve, you see this is a newly designed compound. The organic parts, the atoms which are in the organic part, they are participating in the formation of conduction band. This means that the organic part is now interacting with the inorganic part. So now the interaction between these two are in the newly designed compound is stronger than the compared to the bare one. Okay, and this can also be visualized by this diagram. This electron density diagram, where you can see that see there is no effect, but if you see the part where the organic cations are located, see here the iodine is basically interacting with the hydrogens strongly compared to in the newly designed compound compared to the pure one, which is shown in this figure 4b. And if you see here figure 4e, this is the same case in the newly designed one. So this interaction is more strong compared to the original one. So this means that the stability is getting improved in terms of interaction between organic and inorganic cations in the newly designed perovskite material. Then here this can also be visualized by this by these structure. You see here in this MaPbI3, you have the organic cation forms only 3 hydrogen bonds, and they are also weak. But here in the newly designed case, the second one is the newly designed one, and here the hydrogen bond formation is more. Actually, it forms more hydrogen bond with this inorganic case, and therefore the stability is basically enhanced. This can also be verified by calculating this reaction enthalpy of the formation of these two compounds. You see here the first case, the first is representing the enthalpy calculation for the CS3NH3 PBI3, and this one is the newly designed compound, which is CS3NH2F PBI3, and this compound is the stability of this compound is higher by 1.4 electron volt compared to the original one. So the stability here is enhanced, okay, compared to the pure one. So one part is resolved. Okay, now the another part is the optical property. Okay, see whether if we replace this CS3NH3 PBI3 by this newly designed compound, can we enhance the efficiency of the solar cell? And we can say yes. If you look at this absorption spectrum, the blue one is The blue one shows the absorption behavior by this CS3 NH2 NH3 PBI3. Okay, this is the methyl ammonium lead iodide, the pure one. And this green one, the absorption curve shown by green one, represents the absorption by the newly designed. As we see, here the absorption area has been increased. It means that this newly designed compound will absorb more energy compared to the I mean the CS3 NH3 PBI3, and therefore its efficiency will be obviously high compared to the MAPBI3. So this in this part we have already resolved the stability, which is also improved by this newly designed material, and then energy harvesting from the sun, that also got improved because this absorption area is increased compared to the original methyl ammonium lead iodide peroxide. So this part is nicely presented in this work. Now then the second part is that this stability can also be improved by designing this electron transport or hole transport layer, which I have already discussed. Now, in this case, I have designed electron transport layer, and the property of this electron transport layer is that it should be planar. The material should be soluble in hydrophobic solvent. The conduction band A's of this molecule must exist slightly below that of the peroxide, and its valence band H must exist appreciably below the valence band A's of the peroxide to reflect the photo generated hole in the peroxide layer. It should have the high conductivity for electron, and then the UV-Vis absorption must be high, must be wide. So wide means that it should not absorb, because this is pasted over the peroxide, that is active material, okay, over the active material. So if this should be designed in such a manner that it should not absorb the light that peroxide material gets absorbed. So we have to always take care of it, and we have to design the material electron transport layer accordingly, okay. And therefore you see here, if you look at this slide structure, okay, see the peroxide is at the middle, then there is a HTL, which is a whole transport layer, and then there is a material which is AU, which is which act as an electrode material, then electron transport layer at the below, okay. And then see here, this electron transport layer, this is the energy of the highest occupied molecular orbital, and this is the lowest occupied molecular orbital. So see, this is the peroxide energy, So for ETL, so molecule which act as the ETL, this energy, this age must lie below to this peroxide, and for the HTL, this must be above the peroxide, okay. So this have based on this, I have designed a material which is a well-known material. This nickel pantholocyanamines, that is NIPC, is the short form. And what I have done is a well-studied material as a electron transport layer, okay. So what I have done, I have actually replaced this the hydrogen by this by this anions, okay. So we see here the NIPC are p-type organic semiconductors. However, the substitution of different electron extracting groups like CN, CF3, halogens, and other functional groups are used to facilitate its working as an N-type semiconductor. So if you replace the hydrogen by these group, this molecule started working as a N-type semiconducting molecule, okay. And here what I have done is I have replaced the H by these halogens, by mainly from fluorine, chlorine, bromine, and iodine, and try to study its optical as well as electron transport behavior, so that we can improve the stability as well as the ion transport ability in the peroxide solar cell. And for this, these are the optimized structures. This is the pure NIPC, which has been thoroughly investigated as a electron transport layer. Here, these four are the newly designed, I mean, electron transport layer. Okay. Here, see how to check whether these structure act as a electron transport layer or not. So see here, this is the I mean A's of energy A's for the conduction band, and this is the energy A's of the valence band for the perovskites. And you know, these are the homo-LUMO orbital distribution of pure NIPC and its newly designed derivatives, where we have replaced the hydrogen by these halogen atoms. And you see here, this NIPC is basically the whole transport layer, because whole transport. Why? Because you know, the valence, the conduction age is above than this conduction age of this normal perovskite, and the valence is even also at the top. Okay, so this criteria is for the whole transport. Now for our design molecule, see, this is, you know, the conduction age is lying slightly below the conduction age of the normal perovskite. Okay, so this means that all these design molecules act as an electron transport layer. So this shows that the design molecules act as a electron transport layer. But then we have to check that other properties like optical properties and the electron transport ability of these designed electron transport molecules. Here we have calculated the optical properties, and we found, see, this table actually shows the different values. This is EH is the EH represent the I mean the whole energy is, and this is the EL. This is the difference between these two will give you the optical band gap, and corresponding to this band gap, the wavelength will be shown in this particular column, which is you know, in this table. And then this is the excitation energy for lowest excited state, which corresponds to this I mean particular lambda value. And I mean, this is the absorption maxima actually for this, but all these molecules. And you know, this the homo-LUMO transition is basically I mean possibility of this homo-LUMO transition is calculated by calculating this oscillator strength. And then if the more oscillator strength is basically I mean telling that there will be more probability of this electron and I mean hole to sorry, this conduction band to valence band transition. Okay, I mean this homo-LUMO to LUMO transition. Now in this case, you know, see the absorption, you look at this absorption, you know, so the absorption is wide, and it is, you know, it is completely this absorption is not in the range that our perovskite material absorb the sunlight. Oh, because if it is the case, then the efficiency obviously will be reduced, because most of the light will be absorbed by this the electron transport layer. So this is also well satisfied that this transport material, if ETL material is not absorbing the light where our perovskite material is absorbing. So this one criteria is well I mean satisfied in this case. Now look at the reorganization energy, because the reorganization energy is required to remove or an electron or basically I mean give an electron to the molecule. And you know, this change in energy is basically associated with the relaxation in the geometry, because if you remove one electron, the whole structure obviously will get modified. And therefore how fast this I mean how this fast the molecule is returning to its original structure, that is basically I mean decided by this reorganization energy. And this for this you know for the better performance the reorganization energy must be lower. So if you see here for the electron transport layer, this is now reducing, so in the NIPC it was 0.33, and then for our design system it is reducing, okay, and it is even smaller in case of this iodine dope NIPC. Okay, so this also is well satisfied in our design ETL material. Now here the solubility, because in order to put this electron transport layer, we have to get this dissolved in certain solution. So we have to check the solubility, and solubility of these design materials are good in this DCM and this DMSO. The dipole moment here you see the dipole moment of this original NIPC is basically 0.004, and then in this case it got increased, but in case of this chlorine it is even less, and then in case of iodine it is even lesser than much more less than the original NIPC. Here, why this dipole moment is also needed, because if you have a highly polarized ETL molecule, then it will basically interact with the water, and therefore when it will interact with the water, then there is a chance that this degrade the perovskite also. So we have to design this ETL in such a manner that it has less affinity for the interaction with the water molecule. Okay, so this we have to take care of while designing this electron transport layer. And we check the hole mobility and the electron mobility. So I will not talking of the hole mobility, but we check about the electron mobility. So electron mobility here in case of bromine, it is much more compared to the other design material. So here what I have done is as I said, that this, in order to check whether this design material is hydrophobic in nature, we have studied the interaction of this compound with the water molecule, and we found that if you see that the OH length, if the molecule is interacting with the hydrogen, it means that the OH bond will obviously should change. But here there is no change in the OH bond length. This means that this particular system is not interacting at all, or it has a very poor interacting affinity with this water molecule, and therefore this is well suited as an electron transport layer because it is hydrophobic in nature. Now look by taking this as a ETL bromine, because in case of bromine the electron transport ability was very high. So I took it as simulating the power conversion efficiency of the solar cell. Okay, and by designing, when you use this titanium oxide as a electron transport layer of certain thickness, and then this PCE turns out to be 28, okay, 0.64. And in case with this newly designed molecule, which is as a ETL, this has enhanced to 29.56. Although this increase is very less, I agree that this increase is very less because efficiency is not improved much, but its hydrophobic nature of this particular design molecule makes this this perovskite solar cell more stable compared to what stability one can have from by designing TI2 as an electron transport layer. So in that extent, this design molecule is relatively better compared to the TiO2, which has been used as an electron transport layer in making this perovskite solar cell. So these are the way one can improve the stability as well as the efficiency of the perovskite solar cells. Okay, so this is one can conclude here that the main conclusion of this particular point is topic is that amount of charge transfer here is more compared to the TiO2, and therefore the efficiency is enhanced a little bit. But here the stability is enhanced more because this design material is more hydrophobic compared to the TiO2. Okay, so this is the first part of my talk. Now the second part is the energy storage. Okay, I think I have time, and within the time I'm going to close it. Okay, so this the second part is the energy storage. Okay, so in energy storage, as we all know that because as the energy produced by non-conventional energy sources is in the form of intermittent. I mean, this is basically regional. Basically, somewhere you have sun, somewhere you don't have sun. So in daytime you have sun, in night you don't have sun. So how you can use that energy in the night? So for that you need to store your energy in the daytime, and then you can use it later on in the night. Okay, so therefore we need to develop the energy storage device to store the energy which has been harvested by from the sun, actually by the solar cell. And therefore, as an energy storage system, we know two devices. One is basically battery, which is well known and it's well described, well studied, which has high energy density, high storage capability, and low self discharge. Okay, but it has certain drawbacks, and the drawbacks are it takes a lot of time in charging and recharging. Then the power capability, cyclic life is also not so good, and transportation and safety is one of the more challenging part with this battery. So in order to avoid this, one another device is basically designed that is given a name which we call supercapacitor. So why we call capacitor? Why we call it supercapacitor? Because it is basically a kind of capacitor where the capacitor. What we do, we put a plate and we connect the plates, two plate parallel plates by a battery, and then it is stored charge. Okay, so if somehow if you make a mechanism that somehow we can enhance this charge storage, then that will be called supercapacitor. That's very simple, because it is something which is storing the charge more than the capacitor, and therefore we call it supercapacitor. So in case of supercapacitor, it has high power density, a fast charging time, better cyclic stability, high efficiency. These are the advantages. Okay, so I'm not going in all those details. I'm just going to tell you that how this supercapacitor topic is important for research nowadays, because you see here by year 2022 the global supercapacitor market will be of 2096 US dollar, USD dollar, USD. Okay, so here you have, a lot of, money are going to be basically put for this supercapacitor and for the development of the supercapacitor. Okay, efficient supercapacitor by which one can basically use it as an energy storage device. Now see here for this slide is telling you the basic definition of the supercapacitor. Okay, so here the first one is showing this normal capacitor where the two plates are connected by a battery, and then the energy is stored in the form of electric field between these two plates. Okay, and this C is basically the capacitance is defined by epsilon naught A by D, where A is the area, epsilon naught is the basically the permittivity of free space, and then D is the separation between the plates. Okay, without changing its physical condition, how one can increase its charge storage behavior. And if you design, if you develop this technique, that technique which we call the technique for the supercapacitor. So what we do here, this enhancement of energy can be done by reducing this D. see, if you somehow without changing the physical position of these two plates, if you somehow decrease the distance between the two plates, obviously the capacitance will increase. Okay, and if you increase, so if you in place of this normal plate, if you put a plate that is made up of nanomaterials, which supposed to have high surface area, then this capacitance can be improved even further. Okay, so this technique is used to design supercapacitor. And here you see, in this case, the supercapacitors basically look like a capacitor, but it capacitance as capacitance value and the energy density are very high compared to the normal capacitor. Why it is so? Because it forms if you have two plates like two electrode, and you connect to the battery poles. So what will happen if you put here in the space if electrolyte, then what will happen? So this the positive ion will be attracted towards the negative pole of the battery, and then the positive one will be attracted towards the positive pole, and will form kind of layer of ions close to the both the charge collector. Okay, and therefore this way this distance between these two plates will be reduced. The surface area obviously is more compared to the normal plate, and therefore here the efficiency or the capacitance will be enhanced. Okay, now this is the mechanism how this supercapacitor works. Now see, this supercapacitor is divided into different categories. One is basically double layered capacitor, which the figure which I have shown, that is an example of a double layer capacitor where charge is stored electrostatically. Okay, and this called is EDLC. Okay, electric double layer capacitor. One is the pseudo capacitor where the charge is stored electrochemically. Okay, so then it means in this pseudo capacitor, the transfer of charge takes place through the redox molecules on the surface of electrode. Okay, so this actually is different than the EDLC, and therefore this capacitor is known as pseudo capacitor. I'm not going in that detail because you can find in many review paper where these are well defined. Then if you combine these, so this double EDLC has some advantages and some disadvantages. Here pseudo capacitor also has certain advantages and certain disadvantages. So if you combine these two, it give another category which we call hybrid supercapacitor. And here the disadvantage of these two can be basically removed or can be minimized in some extent by designing this kind of supercapacitor, which is hybrid in nature. So it has both the mechanism that is EDLC type as well as the pseudo type. Okay, so here advantage and disadvantage, it also has advantage and disadvantage, but since research is a process where you can improve the properties of the the design materials further and further. So in this case, I have designed. I took charcoal as a raw material to synthesize graphene quantum dots, and I used these graphene quantum dots as a flexible supercapacitor. Electrode material for energy storage. Okay, so what I have done in this case, in this case, this is this slide shows the synthesis of the graphene quantum dot, where there are so many steps. All the details you can find in this paper, which is published in the New Journal of Chemistry. Okay, so I'm not going that detail. So here, a new process is basically adopted to synthesize the graphene quantum dot using the charcoal as a raw material. The synthesized material was characterized by different techniques like XRD, TAME, Raman, and FTIR, and then electrochemical investigation is done by this electrical and chemical measurement. So here, see the XRD, the charcoal here, the XRD pattern of the synthesized graphene quantum dot is shown in figure 1. Figure 1, the peak at 2 theta, 23.04 and 42.98 are basically assigned to 002 and 100 plane respectively of graphene. Okay, and this has the lattice spacing. This 002 plane has the lattice spacing of 0.38 nanometer. The TAME and HR-TAME images are shown in this figure 2A, B, C, and D. So here you see this is the pure charcoal, and here you see there are dots actually, and I have calculated the size using this particle size distribution diagram, and we found that the average size of the quantum dot is found to be 5 nanometer. Okay, so here look at this. This is even more. The structure of this graphene quantum dots at high resolution. This ACD pattern shows a ring, and this means that it shows the structure is is similar to what we have seen the structure of graphene. See here, we can see in HR-TAME there are the layer can the planes can easily be visualized, and the distance between the planes, two planes are measured to be 0.32 nanometer, which is close to what we have determined using this XRD. Then this the Raman measurement has also been done in order to characterize this graphene quantum dot. And if you see, it has two bands, D and G. In the original charcoal, the G band intensity is more and defect is less. But if you basically if you basically synthesize graphene quantum dots or any graphene based material, like even reduced graphene, this defects intensity should be high. That represents that that you have somehow worked with this graphite, and then some of the part has been converted into the graphene, and therefore this ID by IZ ratio must be high in case of modified graphite. And in our case, it is 0.996. This means that this graphite has modified and it converted into a graphene-like structure. So this has been also verified by this Raman measurement. So in the FTIR also, one can easily see the presence of C double bond C that also reflects that that the planar structure of sp2 hybridized carbon has been formed in the synthesized structure. This further can be that the same thing is further confirmed by the XPS measurement, and we see the energy corresponding to C double bond C is the intensity is very high. This means that the graphite, this quantum dot structure has been formed with carbons connected to this sp2 hybridized manner. And so these are the characterizations that tell that the graphene quantum dots have been synthesized. Okay, and now this is the electrochemical measurements. So these are the results of the electrochemical measurements. If you see here, the first one is showing that that the potential range is basically for it is lying from this this I mean this more than minus 0.1, and then it is up to 0. So this potential window is set, and in that the curve B is showing the CV curve of the graphene quantum dot as electrode material. It shows quasi rectangular like shape that corresponds to the EDLC type electrode with some pseudo capacitive behavior in it. Figure 4b shows that how this capacitance is changing. Specific capacitance is changing with scan rate, and as you know that this decrease here we observe that that there is a decrease in the specific capacitance with the scan rate, okay, which confirm that the better capacity performance of the electrode material. The here further here the same thing is being characterized by this GCD measurement, and if you see here the at high here we can see that in GCD measurement the triangular shape indicates the presence of EDLC nature of our electrode material. Okay, the SC value of graphene quantum dots, based electrode material are calculated at different scan rate, and at 3 ampere per gram, then the value of this specific capacitance is calculated to be 257 farad per gram. Okay, and here the cyclic curve this shows the stability of the this as a the graphene quantum dot as electrode material, and you see here this stability retains to be 96% after 3000 cycle. Okay, here here you see here we for understanding this kinetic behavior of this graphene quantum dots, electrode EIS measurement is also done, and you see here this measurement has two parts, and so you might be knowing that one part is basically having a semicircle, and another part semicircle at higher frequency region, and a semicircle at high frequency, and then slanting line towards this low frequency region. This semicircle is used to calculate that how much resistance this electrode offers, and we calculated the resistance. I have not written here, but if I remember correctly, this resistance, charge sample resistance, turns out to be let me remember it. It is, I think, 1.21 ohm, and the solution, the charge, the resistance offered by this electrode material and contact resistance, that is, I think, 2.72. You can see it also here by this diagram. Okay, so based on this electrode material, we designed a device, a flexible device, and the electrochemical behavior of this device is also characterized using this electrochemical measurements. The first shows the CV curve, where we see the CV curve at the different scan rate, and then again it shows the B shows the GCD curve, and both basically represent that the capacity for EDLC type feature of this device. And you see here, this is the EIS measurement, where we can see that there is a clear semicircle, and then there is a enhancement here in other part, and this using all these measurements, we calculated the energy density and the power density and the energy density of this device is calculated to be 17.36 watt hour per kg, and this the power density turns out to be 191 watt per kg. So as I said, that device is flexible in nature. So here I have basically folded it, bend it at different angle, and try to check whether any change in this CV behavior is coming or not. And we found that this bending does not affect the CV curve of this particular device. This means that its flexibility is well accepted, and this device can be used as a flexible device in order to store the energy. In order to store the energy. Okay. Now here this shows the Rogan plot, and this this result is better than whatever has been reported as a carbon electrode material carbon as a electrode material. Okay, and in our case the value is relatively better than what has been reported in previous reports. Okay, so in order to see the real application of this device, we have basically illuminated red color light emitting diode by charging a device only by few seconds. I think it's 15 or 20 seconds. We charge the device, and this charge device illuminated this LED for 5 minutes. Okay, so this is all about the talk. I starting from this energy storage, starting from this energy harvesting, and then how one can store. We have discussed in this particular talk. So thank you so much. Now I open all of you to ask the question based on whatever I discussed. Thank you so much, sir.
Okay, that's good one, Dr. Ojha ji. You have covered so many things.
Yeah, this is. Let me first show this. These are the. These work have been done by my students and my collaborators. So here the blue line, the blue color names are basically my collaborator, and then the names written by black color actually are my former PhD students. And obviously the financial support. I received the financial support from CSIR, DST, Alexander von Humboldt Foundation, Germany, and then obviously DFG also. And then at last, I know that this talk is always boring, so I have put an entertaining photo, which I found from this photo gallery. And look at this. Thank you so much.
So Dr. Ojha is having so many collaborators. His collaborators from abroad are more than from India. Particularly Germany said that he is having many collaborators, and he has published more than 100 research papers in international journals. They are being cited, and he has organized so many conferences and talks, etc. So now session is open for the questions and discussions. So Abhishek.
Yes, sir.
Yes. Please.
Sir, I asked you one question, please. Hello.
Yes, please.
Sir, what is the main ड्रॉबैक इन सेमी सुपर कैपेसिटर? हम लोग क्या सर गलती कर रहे हैं कि हम उसको अभी तक बना नहीं पा रहे हैं? मतलब सर.
Okay, I got your question.
Yes, sir.
Let me go to the slide. Okay, so look at here. If you see this curve, this figure, where I have plotted this power density and then versus energy density. Okay. So the capacitor, if you talk about the capacitor, so,
Yes, sir.
the energy density is poor, but the
Yes, sir.
power density is high. But
Yes, sir.
in other hand, the battery, if you talk about the battery, the energy density is high, but the
Power
power
density.
density is lower. Now we have to reach here.
Yes, sir.
We have to reach this corner actually. So we have to basically develop a material where we can have, energy density, power density, more, as well as energy density like battery.
Yes, sir.
So I think that will solve our purpose, and the people are trying for it actually. But it has certain limitations also, because while designing this supercapacitor, a lot of mechanisms are involved, and having control over all those mechanisms is not easy actually. For example, if this double layer capacitor, it has certain limitation, because at a certain limit, this absorption is of ion near to the plate is no more possible. Okay, so then obviously this can't store much more charge. But in here pseudo capacitor also, it has different drawbacks, that you hear this redox process, how fast, how slow this redox process is taking place, and then how it is going to affect this electrode material. If you combine these two, then you have a hybrid supercapacitor, where obviously the stability as well as the efficiency is enhanced. Both are enhanced, but now here having control over these two mechanisms now, this pseudo type as well as the EDSL type, that
Yes,
is
sir.
very tough. And the research are being done in this case in order to reach that particular goal, where we can find a material that can show the power density like capacitor and energy density like battery.
Okay, sir. Thank you, sir.
Yeah.
Thank you.
Questions from the other participants, please.
Yeah, sir, I have one question.
Yeah, please.
Yeah,
Please
myself, Sanjeev Kumar from Punjab Engineering College, Chandigarh.
Yes, sir.
Yeah.
So actually, I have a question that suppose we want to do some work on supercapacitors, like we have prepared the electrode materials and we have characterized the same using XRD, SCM, whatever the techniques. Then for CV and GCD, CD, we required one potential stat.
Yeah.
So other than that, what other things we required? Means what are the other facilities we required to characterize the supercapacitor?
Yeah, very good question. Very good question that you have raised. Yeah.
Yeah. See, as far as I know, actually, so see, the normal techniques which you have just spelled out, like XRD, TM, and blah blah, that actually are used to characterize your material. So whether the material which you actually wanted to synthesize, that has been synthesized or not, that has been made or not. So that's one thing. Now another is basically the electrochemical measurements. Okay, so in order to do this electrochemical measurements, you have this electrostat. And the electrostat, you can find, all these this CV and the EIS measurement or GCD measurement, this you can do. Even all sort of measurements which you can do using this this electrostat. As far as I know, obviously, if you are going to the device level, that is true. If you are going to the device level, you need to have a very clean room, and all these manufacturing part that has to be kept in a very well designed or well defined environment.
Correct, Dr. Ojha, thank you. One more query I have.
Yeah, certainly.
Like in the case of potential stat, we are using 3 electrode cell.
Yeah.
Right, and in the 3 electrode, we are using working electrode for our particular material to be characterized.
Yeah.
Right? So means suppose we have prepared some powder of some oxide material or the combination of with the graphene or some oxide material, then we have to make some slurry and then we have to apply the same on the working electrode. Is it correct?
Oh, I did not get your question actually.
Okay, yeah, my question is, suppose we have prepared some material, some electrode material for a supercapacitor.
Yeah.
Now I want to characterize this like I want to find its CV and charging discharging curves. So suppose I have a powder. So first of all, I have to make some slurry by using some organic solvent to dissolve.
That's true. Yeah, agree.
Right? And after that, I have to dry it for some time and then have to apply that on the working electrode.
Yeah.
Right. So I have a problem that how to apply that on the working electrode basically to characterize.
Okay. So, here, I mean, in most of the cases, people are using this nickel foam.
Okay.
So what you do is you synthesize your I mean this electrode over the nickel foam.
Correct. Okay. Thank you.
Okay. And then if you put then initially we were also having the same issue, and then we look into the literature and we found if we somehow if somehow we synthesize this over this nickel we can easily get this electrode work in this particular electrolyte solution.
Right. Okay. Thank you, Dr. Ojha. Thank you,
sir. Thank you.
Any other question, please?
Yes, sir. Myself, Priyanka Moore. I have few questions. First question is, what is the difference between research label efficiency and device label efficiency?
So that is a really good question. See, device is a different part. If you have an electrode and at electrode you are basically characterizing it, you are studying its electrochemical properties by this electrode set. Okay, then you have there you have not to prepare design make it as a device. You are just having this electrode as a bare electrode, and how this electrode is performing. Okay, this you are studying in a normal way. But when you make this as a device, let's say you have you put this electrode material as a device, and then you check how much efficiency you are getting from it. Okay. Then you can have the efficiency at the device level.
Okay, sir.
Yeah.
And my another question is, what is the physical significance of homo-LUMO gap factor?
Okay, see, though physical significance means whenever you are basically calculating
AC connect करता है, AC को ऑफ करता है, बेंड नहीं कर रहे हैं.
May I answer now?
Yes, sir.
Yeah, okay. So this HOMO and LUMO, so the highest occupied molecular orbital and lowest unoccupied molecular orbital. So the highest occupied molecular orbital is basically is the age of the conduction band, and the lowest unoccupied. So lowest unoccupied molecular orbital is basically the another one. So the difference between these two will give you the optical band gap.
Yes, sir.
I mean, you have, in the molecule, you have molecular orbitals. So you have vacant orbitals, you have filled orbitals. So the vacant one will represent the conduction band, and the filled one represent the valence band. So the difference between these two will give you the optical band. This is the physical significance.
Actually, sir, you told that homo-lumo band gap is used for the verification of a peroxide structure. How can means if a band gap comes some range, yeah,
Okay,
उससे relate.
I got your question. See, the idea is that okay, if you talk about the designing a material as a perovskite structure, then so many factors were initially introduced. Okay, but they were not basically, I mean, good enough to to I mean to explain some I mean ABXC type of materials. Okay, so what I did, I thought, okay, if somehow, and all those factors were based on extrinsic property of the material, not intrinsic. Means the physical properties like radius and the volume and all. But then this change when you change the molecule. Okay, so I thought, okay,
Yes.
let us I mean think of some intrinsic properties of that ion. So the intrinsic property which I took as a band gap. So band gap is fixed. So homo-lumo gap is not going to be changed for a particular ion. So I thought if
Yes.
we take it as a parameter, and we formulate a factor using this, then I think we may be successful in predicting the perovskite formation of perovskite structure. And what we have done, and I mean, we get success in that.
Okay, sir. And my another question is, in a hybrid supercapacitor, it is the combination of both electric double layer and pseudo capacitance. Then
Yes, yes.
how can total capacitance is given? Does it is series combination or parallel
Oh,
combination, or it
this
different
is
for different
So
materials?
this I mean, obviously that you have to be calculated using the techniques which you use to calculate for in case of EDLC or pseudo. But the contribution actually can be calculated using the expression. That expression I have not mentioned here. You can find in any paper that is obviously given in there.
Okay, okay. Thank you, sir.
So, any other question, please? Dr. Ojha, that let the other participants will prepare some question. So, a lot of researches are going on perovskite solar cell, that is PSCs. So, how to design energy harvesting materials for its application in PSCs?
Yeah, sir, as I said, that while designing this energy harvesting material, we have to somehow focus first the how that material has the optical band gap. So this band gap must be lying in the range of this visible region. Okay, and so the optics must be clear, that optics must be in the range of visible region. It's starting from this 1.5 to I mean more, and below this I think the I mean that material will not harvest sunlight, because it will be the band gap will fall in the ultraviolet region. Okay, so it will not absorb the energy. So first we have to see this optical band gap of the design material, and then we have to check, okay, if we put this material, this particular material inside inside this inorganic cavity, then how this stability of this perovskite is evolved. So whether it is stability is reduced or it is basically enhanced. So that you have to take care of, and this in order to increase this stability, the interaction between organic part as well as inorganic part, these must be strengthened, must be more. So if somehow, if somehow this extraction is more, then this this perovskite structure that will have less affinity to interact with the outside molecule.
Yeah.
So therefore, this stability can be enhanced.
So, other participants, please come forward if you are having any question. Please don't hesitate in raising the question. So, Dr. Ojha, in PSCs, if you want to improve the stability, then what should we do? How to improve the stability of
Yes,
PSC?
sir. Yes, sir. There are two ways to improve the stability.
Yeah.
I'm just taking the example of this methyl ammonium lead iodide peroxide solar cell.
Yeah.
It is a class of hybrid peroxide. It has organic part in the cavity, and outside you have inorganic part. So as you said that one is to select this organic part which is more polarized in nature. So if its dipole moment is more, it will polarize the inorganic part of the lattice. And as it will polarize now, it will be interacting strongly. So when it interacts now, its stability will be more. This is the first. This is the one part which I have done, and I published it in the Journal of Physical Chemistry. This is the one part. The another part is by designing this better electron transport layer. So this electron transport layer. If you go back to my slide, I can show you. If you design, see, this is here you have
that we have seen.
Yeah, this electron transport layer, Hall transport layer. So this electron transport layer, because it is in between, the peroxide molecule is in between. So this ETL has to be designed in such a manner that is in a manner that it should be hydrophobic in nature.
Yeah.
But it should not interact with the water.
Yeah.
Okay, so it has less affinity for the interaction of water, and this I have already achieved actually. In this case, that if you see here, in this case, the affinity with the water of this molecule is very, very poor, because there is no change in the OH bond. Because hydrogen bond form, when the hydrogen bond is formed, then OH bond length obviously will get modified. But in this case, it is not happening. This means that this molecule is not interacting with water. It means that it has a very less affinity with the interaction of water, and therefore this will protect this peroxide for the degradation. So this way one can enhance the stability.
Yeah, that's good one. That's very good one. Very well that you have explained. Sunil Kumar Sharma, probably he want to ask some questions. Sunil, whether you want to ask some question? One Mr. Sunil Kumar Sharma, probably that his mic is on. You want to ask some question? No.
Actually, I thought that this much slides will be enough for one and a half hour lecture, and then half hour. Yeah.
Okay. You are having vast experience, so there is no problem. So let us discuss something more here in PSC.
Yeah.
That stability improvement that we have seen. So after that, there is another question related to this one, that how to improve the efficiency of PSCs.
Yeah. So this efficiency is really very interesting. Property, that how to increase the efficiency. Now, for enhancing the efficiency, we have to basically, as I said, sir, initially, that in the perovskite, when you make the perovskite solar cell, we use perovskite as a energy harvesting material.
Yeah.
So I mean, if your perovskite molecule absorbs much more light,
Yeah.
then there will be a chance that that particular, I mean, if it absorbs more energy, then there will be a chance that the energy will be converted into the electrical energy.
Yeah.
And therefore accordingly the efficiency will increase.
Yeah.
The same thing one can apply here also. I mean, here the designing part plays a very important role in this research actually. Either you are working in supercapacitor or you are working in this perovskite solar cell. The designing of material, I mean, you can't take the material arbitrarily.
Yeah.
There must be logic behind it, that what material you are going to take and then why, and what we are going to get from the if we use this material as a superconducting material or a perovskite material. So again, sir, again I'm saying that this designing of molecule, that is the energy harvesting molecule which harvests the energy, that is very, very crucial. Its optical feature has to be calculated, has to be studied very nicely. And if this absorption area, if the absorption feature, if the molecule that absorbs much more energy in the visible region, this means that the efficiency obviously will be more for that particular sky solar cell. So here the most important part is the designing of the molecule. Then it's not only the perovskite molecule which absorb the sunlight, sir. ETL also, electron transport layer. So if you are designing whole transport layer or electron transport layer, so the whole mobility must be high for the whole layer transport layer, and the electron mobility for the electron transport layer, that also must be high. Then it will be basically contributing to the continuous flow of the electron and hole, and then the efficiency obviously will be getting enhanced.
Yeah. So hole and this electron, that is mobility will increase, then certainly its efficiency is going to increase.
So there are several factors, sir. It's not only one. So we have to optimize actually. We have to optimize these conditions.
So any other question from the participant side? Yeah, one person that he want to ask.
Yes, please.
First of all, I would like to thank the speaker for his informative talk. I want to know what factors controls the maximum charging cycle for these kind of devices.
Charging cycle, you are talking of this.
How many times such batteries can be recharged?
Okay, you are talking of the battery. Great. See, I mean this stability is very, very important. I mean, like any battery or any energy storage device has a certain life, so you can't I mean charge it or renew it in an infinite number of times. So this actually this is decided by the chemical composition, of the battery. Like if you talk about the supercapacitor, so you have like I'm talking of EDLC type. So what you have an electrolyte, you have a positive plate, you have a negative plate. The electrolyte gets ionized. You have a positive ion, you have a negative ion. So the positive ion will be attracted towards the negative plate, and I mean the negative ions will be attracted towards the positive plate. Now think about the situation when there is no ions left. Then what will happen? So that device will reach to its maximum capacitance. Okay, and therefore that capacitance of that particular device cannot be enhanced further. So this actually, keep on decreasing with the time, and therefore this is why the stability of such devices are required to be improved, so that we can use it for the different purposes like battery.
Yeah, that's good one. That's good one. So any other question, please? In MS Team, there is an option that you can raise your hands. So if you want to ask any question, then please raise the hands.
Ravi, did you get my answer?
Probably you can continue now. Yeah.
Yeah, thank you, sir. I got the answer.
Okay. Thank you.
So, is there any other question, please? So, if there is no, yeah, Ajay Singh, okay, please.
Sir, I did not get your question.
Ajay Singh, you can repeat your question, please. Ajay Singh. Ajay Singh, please repeat your question. Ajay Singh, please repeat your questions. No, probably that he is unable to listen us. Yeah, maybe some connection problem is there.
Okay, yeah.
Some connection problem will be there.
Yes.
Any other participants, please? So, if there is no further question, then let us thank the speaker. That's very good talk that he has given today. Very informative one. Designing of materials for the solar energy harvesting and energy storage. So, the next speaker is Dr. A.L. Sharma. He will start at 5:15 p.m. So, we will join this meeting at 5:15 p.m.
Okay, sir. Thank you.
Yeah, very good picture.
Thank you, sir.
Here, Jallas and Taman are here. Holi festival that you are
Just to make audience relax, na.
Yeah.
Because it's a 2 hours talk is a boring actually sometimes.
Jallas and Naman, very good.
Okay, sir. Thank you so much. Thank you so much, sir.
Okay, welcome. So, okay, let us stop here, and we will again join at 5:15 p.m.
Thank you, sir.
Okay, welcome, sir. Welcome. Very good.